Well, before we'll start the seminar, I have a small announcement. This announcement is related to what we had last Wednesday. As you remember, last week was full of conferences. First, we had on Monday Cyfronet Open Day. Then on Wednesday there was a full-day conference of Sano Scientific Day, and after that we have Life Science Open Space organized by Cluster Life Science and Sano conference in Collegium Maximum of Jagiellonian University. And during SanoScience Day, besides of talks, all talks were plenary. Besides of talks, we had exhibition of 22 posters of our PhD students, and there was a kind of competition, selection of the best poster, and I would like to announce that the best poster recognized by number of votes, which was, let's say, 2 times more in the next poster, the second one. So the best poster was poster prepared by Dominika Ciupek with co-authors Jan Fischer, Maciej Malarski, and Tomasz Pięciak about the grasping the microstructural parameters of the brain in a heterogeneous multi-site environment, a federated learning approach. Congratulations to Dominika, and I hope that it was the most important to announce the winner, and we will award will come soon. Okay, so I think that it is 4 minutes after 2, so we can start our seminar. And well, in December we decided to have 3 seminars on Nobel Prizes, and the first one will be about Nobel Prize in Physics. The author of this seminar, the presenter, is Dr. Karol. Karol is a postdoc in Sano Center for Computational Medicine, and he is also a staff member of the Faculty of Computer Science at the AGH University in Krakow. Well, before Karol will start talking, if you have an urgent question, in the room, ask simply Karol. And if you have urgent questions online, please write this question in questions and answers part, and questions or answers, or maybe if not questions or answers in chat. I will try to look at both of them, and I will transfer this question to Karol. Well, besides of these questions during Karol's talk, we will have, as usual, discussion after the talk. So, well, that's all for introduction. And Karol, floor and screen are yours.
Thank you, and hello, everyone. So the topic, of course, is this year Nobel Prize in Physics, and you can go to this topic in at least 3 different directions. But because of the fact that is from physics and I am physicist, it will be focused on the physics side of these problems. And because I will talk to the audience with the very diverse background, I want to start with some introduction to some basic model, which is starting point for the whole discussion about this Nobel Prize. And then I will go through two main models which were awarded this year. So when this prize was announced this year, there was a lot of questions, consideration, is it physics or not? But I, instead of like trying to have my opinion just based on the title, I decided to go to the Nobel Prize Committee website, and there is the comment like that, which explains reasons which were behind the decision. And it's a very good starting point for someone who understands math or physics at some intermediate level to try to investigate the reason of this Nobel Prize. If someone does not feel well enough in this field, there is also more popular science version, which I then encourage to check. This was like definitely my starting point for this seminar. And I, as I said, encourage to check it if you are interested. So, as I said, I want to start by introducing you to the Ising model, the most basic statistical physics model, or which is also based for the rewarded works. And first, starting with some maybe intuition. Imagine that you have like two magnets. Usually they want to set in the way that they are parallel one to another. So like in these pictures where the field forces the magnet to set it like that. So you can for some reason imagine that there is one arrow here, one arrow here up, and for example, they are pushed to be in the same direction. But and if they can't rotate around, just be in the position like these two positions shown, like 1 and 2nd, you can just represent it by arrow. And such object called spin, as I said, can be in one of two states. One, or you can call it up, and for example, I-1 and I+1 are up, and usually they are denoted in equations by spin +1. I keep all units, all constants in such a way to have a simplest possible equation, so please keep it in mind. Or it can be in the state down, like spin I, which is denoted by -1. And as I tried to discuss before on this intuitive example of magnets, these spins want to be ordered in such a way that everyone is in the same direction as both of their neighbors. So in this case, the spin I is very unhappy and would like to flip to, or in more general way, if they want to be in the one way, based on this example, or you can flip 3 of them or 2, and flipping 2 will be just less moves. This is on the intuitive side, but you can express it in the more formal mathematical way. So for our spin I, there are 2 neighbors. Neighbors I minus 1 and neighbor I plus 1. And this is included in its energy simply by multiplying them by each other and some constant which describes strength of the connection. And as you can see, if they are in the same direction, this term has sign minus, and if they are in the different directions, they are in the value is then positive. And so to calculate the whole energy of the one single spin, we need to just calculate how much energy comes from the different neighbors. So we calculated, in this case, both pairs. And in physics, we usually like to minimize something. And usually this thing is energy. So we want this term to be as small as possible. But we want to not only describe it in the terms of one single spin, but in the terms of the whole network. So for the convention reason, here I express an energy of function as h, because in physics usually it's called Hamiltonian. It depends on the spin configuration. That's why it's function of S in the board S. So it's a set of all spins in our network. So all possible i's. And you need to sum it up over all possible pairs, like how we see in the previous slide. Here there's only 2, so everyone has. So there are pairs like that, but the neighborhood does not need to be as simple as on this example. You can have the most popular one is probably square lattice. So you can imagine it as a duplication of this row infinitely in both directions, which are like up and down in the slide. And there the number of neighbors is 4. So there is much more pairs we need to take into account. However, it's also not limited to some simple networks. It can be used, you can have basically any network, any graph you want to. So we want to extend the model a bit. And because spins basically behaves like small magnets, we can consider that there is some external magnetic field P, which interacts with our spins. And again, spins want to be set in the direction dictated by the field. I hope nothing breaks now. Okay, but we can even break it more. So for the discussion for the very simplest for the very simplest setup we shown before, we assume that all connections are equal, but it might not be a case. For example, like in this example with magnets, one pairs of magnets can be further apart each other, and some of them might be closer, so it might change this interaction, or I don't know, magnets might be of the different strength. Anyway, the energy in every connection might differs. So we can introduce it to our model, to the Ising model, but by making the J matrix depends on the indices of the spin. And also, we assume that the field is uniform, but it also does not need to be the case. It might be the situation that the field for every spin for some reason is different. The structure of the field is much more complex than just much more complex and more connected with the structure of the network. So we have basically three cases for the J. One which we know already is the J which is positive, and this was like described at the beginning, that the spins want to align one to another, so be the same sign as between. There is the second case, but there is a second case where the J is negative, and therefore spins want to be oriented oppositely, in opposite orientation. And this case is, for example, case of the real magnets I've shown at the beginning. And finally, they can be the case where Ij is 0, so magnets does not interact with one another, spins does not interact one with another. And this is useful to make our model just simple to present if we can have all connections, but some of them with 0 values. Also, of course, there is a very interesting physics behind all these cases, but it's not exactly the topic of this presentation. And to sum up, to close this introduction part, I need to also introduce some important concepts from statistical physics. So whatever I discussed before, physically is considered as a thermal solution. So like this, our chain is completely outside any environment, and so there is no fluctuation. Everything is just behaves in the very deterministic way. But in physics, statistical physics at least, we usually consider states which are in some kind of equilibrium with the environment. And in case of the canonical ensemble, it's a thermal equilibrium with the environment. So the temperature of the environment is the same as the temperature of the chain of the network. And in this case, we can't say what is the configuration of the spin. We more like to look at the probabilities of the different configurations of spins. And it's given by this not that not terrifying looking function, where in the exponents h is our Hamiltonian I was presenting you so far, and beta is a parameter which is connected to the temperature. It's in proportional to the inverse of the temperature, but it's more often used in this form. And there is this z parameter because it's probability. So we want it to sum up to 1. And therefore you need to calculate it in such a way as a sum over probability of all possible energy of all possible configurations of spin. Yeah, and therefore it's normalization factor. And now, when we have a proper introduction to the basic model, we can slowly try to understand what was done by Hopfield first in networks named after him. So, yeah, this is the, so we have, I just want to remind how the Hamiltonian looks like, and we want to consider again, but in more general case, what is the energy of the given spin for a given spin. So yeah, we can. So we choose the again spin number I. So now it's a constant, so we can put it outside the bracket, and we have this term in the bracket. So energy is minimized when the sign of the spin is the same as the sign of the term inside the bracket. So what can be somewhat intuitively understand as before, we see that we minimize the energy of the regular when the spins were of the same sign. Okay, so we want to calculate how these conditions. So yeah, if we want to have the spin +1, we have this condition, and this is just simple symbol manipulation. We have the condition that the sum of the spins of all neighbors must to be larger than minus beta minus bi. So the external magnetic field. And in the case of S equal -1, of course, it's reverse. So we can use this to introduce the dynamic onto the network. So we can take, for example, random spin, calculate these conditions as were shown, and set up spins based on them. So if the sum of the part coming from the neighbors is larger than this parameter, we keep or change the spin to +1, and otherwise we change it to -1. And we can think, and therefore we can think also about B as some kind of activation value, activation threshold. I know that for some people it might be more intuitive to change it into some other parameters, which is positive, so not -B, it's but some U, like in the Hopfield paper, but it's just question of convention. And also, based on the Hopfield work, we need to add 2 more assumptions. First of them is so-called no self-interaction. So the diagonal elements of the matrix JII are equal 0. So what is somewhat intuitive for physicists that you can't really interact with yourself, it could lead to very pathological behaviors in the system. But there is also a second condition, that the network is in case of, as an indirect graph, or the interaction is symmetric. So it's, if for someone it helps to have some intuition, it's like third Newton law, that if something acts of something else, the something else will act on itself by the same and it force in the case of the law, but in this case, the interaction is also the same. I know that in the non-physical systems, it might not be that obvious, but soon we will discuss why this assumption is important. So we have these constructions, which is named Hopfield network, and what we can do with it. For example, we can store information in this network. And we use it by proper construction of this matrix J. In this case, and to construct it properly, to have to store information inside it, assume we have some set of state sigma, which represents our information. For people more familiar with computer science, I guess it would be zeros and ones, but in this case, for now, it's plus or minus one. And because we know how that energy be minimized when the spins are in the same direction orientation, we can just create this matrix in such a way that we multiply each pair of spins with each other, and therefore, if we put it in the system, they will eventually, the system will transform into the system where the spins are aligned with our original spins. But is it really true that it will finally reach the state? This was one of the questions asked by Hopfield in his papers, and now I need to make a small interview to explain you why you may expect different types of behavior. I decided to do it on the continuous system because they work better for intuition and so help to understand people who are not physicists or mathematicians to understand it. By behavior in the discrete system is somewhat maybe similar in the intuitive way, much more, but different in, of course, mathematical. So we can have, for example, some local minimum of the energy, or so the system which attracts the solution to some point. Wherever you start in this space, you end up in the minimum. But you can have, and this is just a rotation of this first function case, where there is one point which is stable. So if you start exactly at the top of this shape, so in this maximum of this, of course you are stable, but any small movement can send you far away to infinity far of your expected point. And finally, it's not the last, it's just examples to show the different behaviors and why we want to check it. You can, for example, have something like a saddle. It's called a saddle point because it looks like saddle, and you can, so in one direction it tends to this special point, but in other direction it is moved to the infinity. So, And there is more behaviors, and in the discrete system you can, or in continuous I guess also, but you can have cycles which allows you to just jump between two states and never settle in one of them, and so on. So what's with our system? So if we want to change, so when we change the energy of the system by flipping one spin, we have just this term, which is like the difference between the original and non-original state, and of course sum over its neighbors. Yes, I put the external field to 0 to as well as the Hopfield field to simplify the calculations. So, and we see that the function will be decreasing one, and because of how this algorithm of the updating the network was constructed, this energy is can't ever rise, because we always or we do nothing or we switch the state of the network to the lower energy one. So thankfully we can have this behavior I said a bit before, that in the long time our solution will reach the minimum which comes from the spins. And why, and now I can explain you why it's important for our matrix to be symmetric. Consider just as example two-spin system which is directed, and left spin wants to act on the right spin with minus, and the second one with plus. So they want different states. So they will switch between configuration where they are in the same direction and in the opposite direction, and we never reach a stable point, but we end up on the some kind of, I think it was called orbit. And also I need to make some comments of the Hopfield work in this point. So paper was written in the perspective of making a mathematical model of biological neural network, or some kind of electronical storage device but based on this network. And some of you who works with neural networks or with electronical systems might be somewhat disappointed, because these systems are not discrete. The changes are continuous, and this activation is not the threshold, it's an activation function. And yes, this were also consideration which were put, the questions which Hopfield got, because 2 years later he considered also the model which is not discrete but continuous, and he has shown that in terms of the limit behaviors, they are equivalent as long as the activation function is step enough in the vicinity of 0. For his work, he used sigmoid activation function. Yeah, I don't go into details of this derivation, because it's complex, but in the end won't bring anything more to this story than the conclusion that it's equivalent. So now we can move to the second part of the Nobel Prize, and in this case it's Boltzmann machines. So so they start very much from some limitations of Hopfield networks. As I talked before about Ising model, it's as in this representation, it's purely deterministic. There is no randomness, no stochasticity. It's just one deterministic set of solutions, and because data can and yes, and because the world can be noisy and evolution might not be that deterministic, or we don't want it to be that deterministic, we can think about how we can make it more random. So, and in this point, I almost by accident did it in the previous slide. I need to, for a moment, talk about some convention symbols I use to not confuse, because previous works by Hopfield were very much in very physical terms, and therefore it was very natural for me to keep the convention of spin plus minus one. But for people who are more familiar with information, they much more prefer to have it as a zeros or ones. But don't worry, the approaches are very much equivalent, because transformation between one and another case is very simple. It's basically difference of some constant term. So the conclusion achieved so far translate to the systems with just some slides different of the equations. But just because of the language of the work I try to present, now I will somewhat in between these conventions. For example, if you see that I'm saying that the spin is in off state, it means that it's or minus one or zero, depends on the convention or chosen convention, and it's on in the other case. Also, I just want you to remind, if you manage to forget or this canonical ensemble assumption, which was made to introduce the noisiness, the thermal effects on the system. So how we can use it? We know the canonical ensemble, and we know what is the difference of energy, and we want to use it to make some not deterministic rule of evolution of the system. So we can take these probabilities from the canonical ensemble, calculate its ratio. Just because this is only two-state system, probability of being in the state off is just 1 minus probability of being in the states on. And if what can be easily calculated from the previous slide's equation, it's just e to the power beta minus beta and the difference of the energy. So we have basically everything in this equation, and after a simple calculation, we can get the formula for probability of activation of the given spin, so of this flip of the given spin, which for probably some of you who are more familiar with machine learning, it should look somewhat familiar. And how you evolve the system? You just you calculate this probability and then use it in some way as a probability of switching between states, and you introduce therefore the randomness to the system. So for the sake of completeness, Boltzmann machines works basically on this premise. And what is also important, in this place, I leave the part of physics in the understanding I so far used it, but Boltzmann machine is a network, again, what we can see by using of Ising, which is made of two types of nodes. This one in white are named visible, and the blue one are named hidden. So in the sense that we put input to this white one, and we use just the blue one to support any calculation of probabilities and so forth. And to close what was done and what was awarded this year in the Nobel Prize in Physics. A few years later, Boltzmann machine was transformed into restricted Boltzmann machine, where you make basically visible units only connected to the hidden one, and other way around. There is no more interaction between the spins from the same type, the same layer. And so to sum up, this year Nobel Prize was given for the very clever views of the well-known physical model, which is Ising model, which can be simply described by this equation. In this no fluctuation way, it is used as a model of some information storage network in the Hopfield network, but with a noise, it becomes the basics for the Boltzmann machine and the restricted Boltzmann machine. And I think this picture, which is taken, by the way, from the Nobel Prize Committee paper I've shown at the beginning, perfect summation of what was the basics of the Nobel Prize in this year. If you want to read more about it, because it was a very fast summary of many years of research and different papers, first of all, again, I encourage you to start from the scientific background from the Nobel Committee. And there will be a lot of references there, but three I use the most for the presentation are two papers of Hopfield, which I discuss in details, and this one conference paper with many authors, which one of them is this year Nobel Prize winner.
40 years it took him to get the Nobel Prize. Sano is only 5 years, so we've got 35 years.
It's very quick to get so Nobel Prize physics.
Yeah.
And thank you.
Well done.
Thank you very much. Well, we have time for discussion, for questions. So it's time for questions which were not asked during the presentation.
Someone in the live audience wants to ask the question? Okay, Marianne?
Well, I think that one of the important issue here is to demonstrate the fact that the statistical physics gives some tools to assess quality of what is now used as the neural network, in the sense that we have some, let's say, some values which can be calculated and which can, to some extent, explain how neural network works. Yes.
Yes, we also So first of all, the goal of my presentation was shown all this physics background and work for the last basically century, which lead to these systems which ended up being useful for the machine learning, the development of the neural networks. But it's not that surprising that it's important, as the statistical physics works in the very similar language of probabilities and entropies informations as machine learning does.
There are different type of these neural networks. Yes, some of them are called convolutional networks. Sometimes people use this deep learning. Do you think that it would be possible to, or do you know some, let's say, research which enable to evaluate the quality of such a network before it will be constructed using a lot of processors?
I haven't seen research like that. The main problem I see is that you need to analyze the network in a similar way in terms of statistical physics. You need to first know this network, and training of this network is like this most computing extensive part. So I think it's more like useful not to check if but maybe you can make some statistical physics analysis, but I'm not aware of it. But what I'm more sure is that it might be a good starting point for any discussion about analyzing the networks after its creation. What is also important, especially for us in Sano, is it can extend the explainability of what's going on inside the system.
Yes, it's clear. Many thanks. Well, we have time. Kasiu, please ask a question.
Hello. I have a question, very simple, because I'm not very familiar very well with machine learning. Where is input and where is output to these networks? Because I saw the graphs, but I have no idea where is input and output. Where you want to, because I understand machine learning in the way that you have some input and you want to so you for which you know the answer, and then you have input for which you don't know the answer, and you first train the network, so train the weights of the network, and then you give it a input for which you don't know the answer, and then you get the result. Yes, so I cannot get how these graphs are actually related to the actual neural networks.
So, thank you for question. It was somewhat outside the scope what I wanted to talk about, because I wasn't like willing to go into the machine learning problems, as I'm not an expert, and I think I can find in Sano at least dozen of people who will explain this problem better than I. But in this case, what I understand is for Hopfield network, you created this network by storing some information, as I talked before, and then you put some noise inside the network, and you restore the information put at the beginning. So, like the most common and best known binary use of the Hopfield network is more like restoring information which was distorted by some kind of noise, or by this kind of behavior. Any other use, I'm afraid we need to ask someone who is more knowledgeable about machine learning. And in case of Boltzmann machines, had some problems, but they behave basically, both Boltzmann machines and restricted Boltzmann machines behaves very similarly. Input is in these layers which are in this what to say, in this nodes which are named visible. You put the start information inside them as a and then the network evolves, and you get the solution also from the same visible nodes.
So is it correct to think that?
Sorry for a moment.
Yeah.
Can someone go for the charger, because we will be out of energy very soon.
So is it correct to think that it's the mechanisms that allow to process the information inside the network? So the network reads the information that it's capable of under the condition, because you talked about energy, right? But we're talking about the neural networks that processing information under certain condition, and the condition can be that you add in a layer let's say the layer that stores the information, and then the model reaches to, for example, read the picture in a way that it discovers that the picture is a cat or a dog, right?
I guess so, but as I said, my goal was not connected to.
No, I understand, but I'm talking about the question that was asked. So
I'm not sure if you were, if people could hear you online. Marian.
Wait a second. We have Wiesław here online. Yes.
Okay, so we were not heard online.
Yes,
Okay.
yes.
Wiesław, you can ask the questions and present comment.
Okay, thank you. So you nicely explain why Hopfield received his Nobel Prize in Physics, but why Geoffrey Hinton received Nobel Prize in Physics? Because he is known as the father of back projection. Any justification?
So for me, this is somewhat controversial question, in the sense that, first of all, it's easy to understand why Hopfield got the Nobel Prize, because he was the only author of the paper, and it's obvious, therefore, that he was included as we discuss him. In this case, we have 3 authors, but 2 of them are seen in the most of the papers connected to Boltzmann machines. So this is somewhat, but also at some level, the Nobel Prize can become controversial. I think, so these models are still connected to the physics, in the sense that it's still very much interesting use of the statistical physics to create model which can evolve system in the computationally important way. And therefore it was somewhat compatible with the previous work. And as I understand, for the development of the neural network themselves, this input from the second winner was like, I don't know, similarly important, more important. It's more the question to the people who works with neural network than it was to me. But this is how I understand that the first part was more strongly connected in this mathematical tools of physics which were used to create neural networks. And the second one was for making a bridge between this strong mathematical background to the language which was more useful or understandable for people working on the machine learning problems.
Yeah, by the way, the third author, Terry Sejnowski, is of Polish origin. I
Yes.
don't.
To be completely honest, Hopfield is also of Polish origin. I think he was born in Poland, but was raised in USA. But his both parents are from Poland.
Oh, I see. Yeah, I met Terry. I gave a talk in his lab, but it was a long time back. It's interesting that you can get Nobel Prize for the paper, conference paper. Yeah, is it not surprising?
To be completely honest, they listed two papers which were both conference one, and as I understand, there was also all their papers which introduced this, but probably Nobel Committee couldn't get them, and therefore why they were not introduced. As I said, I highly encourage you to check this explanation to really see which papers were Nobel Prize Committee considered as important, because in case of Hopfield, these are for sure these two, while in case of Hinton, it's this paper, but there is also backpropagation mentioned. Like they somewhat mentioned all like these famous achievements in computer science, but I don't elaborate about it because it was not like that strongly connected to physics. That's why I think it's more about the making this translation from the physics to computer science as his input into this Nobel Prize.
By the way, Jeffrey Hinton commented about his back projection, throw it out all and start it again. And he also added, I hope that some clever student will be suspicious about all this stuff and do it much, much better. And anyway, we see that he was maybe not right, or maybe he was too modest. Okay, thank you.
Thank you, Wiesław, for your question and comment. Well,
when we are in the anecdotes also, if you read the story of Hopfield, his surname is just a direct translation of the surname of the parents when they were in Poland, just translated into English. That's how they got their surname. Okay, Marian.
Well, do we have some questions in the room? Because online I have no question.
Any question in the room? Okay, room is
Everybody's scared of asking questions now.
No, well, okay.
Oh, but it's inspiring to think about that.
Okay, so well, it means that that now we know why it was Nobel Prize from Physics, and fortunately, assessment of scientific achievement by Nobel Committee is not exactly the same as assessment of scientific achievements by different scientific units in Poland. So maybe it will be easier. Well, someone can consider that it could be easier to get Nobel Prize than A+. Or anyhow, well, so in this way we know more about Nobel Prize in Physics. In a week we will have another seminar with Tomek Kościółek, who will be talking about Nobel Prize in chemistry, but it is very, very close to biochemistry and biology and life sciences. So it will be in a week from now. Many thanks to all of you for participation, for questions. And well, I invite you to this next seminar, Nobel seminar at Sano. Thank you very much and bye.
Bye. Thank you.